Okay, so the next notion we want to discuss is called linear independence. In fact, there are two notions, linear dependence and linear independence. And I'm going to start by some examples, and then we're going to write the definition. It's going to emerge from the examples. So here's our first example. Suppose we have a general element in R2, okay, AB. It can be written as A times 1, 0 plus B times 0, 1. Do you agree? Okay. So this means that this general element in R2 can be written as a linear combination of 1, 0 and 0, 1. Right? Another way of saying it, tell me if you're following, that AB belongs to the span of 1, 0 and 0, 1. But this was a general element in R2, right? So the conclusion here is that R2 is included in the span of these two guys, and since this is the world, this is V where they live in, there can't be anything else, so it equals the span of 1, 0 and 0, 1. Any element in R2 is a linear combination of these two guys. If you took these two guys out of the sack that contains R2, the vector space that they generate, the subspace that they generate, is in fact everything. Do you agree? Okay? So this is example 1.
Isn't it contained in the span? No?
Yeah, it's contained in the span, but there can't be anything else in the span, because the most that the span can be is the world that it lives in, so in this case it's equal to span. Okay? Okay, here's another example. Let's take AB, a general element in R2. I can write it as A times 1, 0 plus B times 0, 1 plus 0 times 2, 3. Do you agree? Any element in R2 is a linear combination of these three guys. Okay? So we can, just like before, say that R2 is contained in, and therefore equal to, in this case, the span of these three guys. Oops. Do you agree? Now, what's the difference between the first example and the second example? That this dude here, 2, 3, was really not necessary. He was an extra, right? He's coming along, but we don't really need him. Okay? We can throw him out and still have the same span. He doesn't add anything new to the span. Okay? If we look at this span and throw this out, it's a totally different subspace. Right? If we throw 0, 1 out, we only get vectors of the form A0. Right? So adding this vector really throws in a lot more vectors. Right? It really increases the subspace. Whereas throwing this in just doesn't make any difference whatsoever. Do you agree? Okay? So this is the notion that we want to capture. This is the phenomena that we want to capture now. We want to be able to look at a set of elements, of which we think as generating a span, and say, are they all necessary? Do we really need them all, or can we optimize? Can we throw some of them out and still have the same span? Okay, can we throw some out and not really do anything? Are we just taking some extra stuff which we don't really need? Okay, is the question we're asking clear? Okay, so let's summarize the discussion in these two examples, and then we'll say a bit more. Not really needed.
Can we actually say retrospectively that the matrix of 2 and 3 is the scalar of it is 0, while looking at the end.
What do you mean the scalar of it? The span of these guys is all the linear combinations you can write using them. So you can take, for example, 0 times this, plus 0 times this, plus 5 times this. That's also in the span. But it's nothing new. You could have gotten it without this as well. You could have taken 2 times this and 3 times this. Okay? So it's not that any time you write a linear combination, you have to take 0 there. You can take anything you want there, but it's not going to add any new vectors. Clear? Okay. So let's write these ideas. So we want to identify sets of vectors without, let's write it in quote marks, without extra unneeded vectors, where we really need all of them, where all of them are indeed necessary in terms of the span, in terms of adding new stuff to the span. Okay? So what made, let's look back at the example. What made 2, 3 unnecessary? What made him extra?
It's included in the span of the other.
Very good, very good. This vector itself was already a linear combination of the other 2. That's what made him extra, right? We could have written him as a linear combination of these 2, so we don't really need him. Do you agree? So let's write that. 2, 3 was extra, was not necessary, because 2, 3 is a linear combination of the other 2. Okay, we could have generated it from the other 2. We don't need it as a generator. Okay? And this statement can be rewritten, just a different way of writing the same thing, or I'm just rewriting this differently. 2 times 1, 0 plus 3 times 0, 1 minus 1 times 2, 3 equals 0. Do you agree that this is the exact same statement as above? Okay? And this is the notion that we're going to capture. This is the statement. The statement here is that a set includes extras if we can take a linear combination of the elements of the set where not all the coefficients are 0, but still get the 0 vector. That's what happened here. Okay, so here's the definition. Tell me if you agree. The first time you see this definition may look weird, but I want you to agree that it's precisely saying this, which is precisely saying this. So the first thing you have to agree on this example, that saying this and saying this is the same thing. Do you agree? And this is what we want to capture, therefore it's just as good to capture this, right? Do you agree? So definition, v1, v2, up to vk, a set of k vectors, are called linearly dependent if there exist, you know this symbol, right? There exist scalars, alpha 1, alpha 2, all the way up to alpha k, in the field, in F, scalars, not all 0, not all of these can be 0, such that the linear combination with these scalars, alpha 1 v1 plus alpha 2 v2 plus ... alpha k vk, is the 0 vector. the set of these three vectors, 2, 3, 1, 0, and 0, 1, is linearly dependent. There exist non-zero scalars. Well, not all zero scalars, namely 2, 3, and negative 1, such that the linear combination with these scalars, 2 times this one plus 3 times this one minus 1 times this one, gives you 0. Clear? Everybody good? Okay. So in general, suppose here's another way of saying it abstractly, which reflects what just happened in the example. Suppose you have this set, and it's linearly dependent. You can find scalars like this and write this. Then, for example, suppose alpha k is not 0, okay? Then I can write vk as a linear combination of the others. I move it to the other side. I get that minus alpha k vk is the linear combination of the others. And then I divide everything by alpha k. It's not 0. And I got vk as a linear combination of the others. Okay, maybe let's write that. If v1 to vk are linearly dependent by that definition, then at least one of the alphas is not 0, right? Then at least one alpha I is not 0. Do you agree? Because that's the definition, that not all the alpha i's are 0. And then, just like we did in the example, if we take alpha 1 v1 plus alpha 2 v2 plus ... and here I'm taking alpha I minus 1 vi minus 1, and I'm going to move alpha I vi to the other side. So I'm skipping it and writing alpha I plus 1 vi plus 1 plus ... all the way to alpha k vk. This equals minus alpha I vi. Do you agree? I just moved this one to the other side where there was originally just a 0. Good, everybody with me? And then I'm going to divide by minus alpha I, which is not 0, because there has to be one of them that's not 0. Okay, so minus alpha 1 over alpha I v1 plus, minus alpha 2 over alpha I v2 plus ... plus alpha k, or minus alpha k over alpha I vk equals vi. I just expressed vi as a linear combinations of the others. Vi was extra. I didn't really need him. He's generated by the others. Okay? So vi is what we called extra. It's a linear combination of the others. Clear? So is it clear why this definition really captures the phenomena of having an extra guy in the set? Good? Okay. So here's the complement of being linearly dependent, namely being linearly independent definition. V1, V2, up to Vk are called linearly independent if what made them linearly dependent cannot happen. So if whenever we take a linear combination, alpha 1 v1 plus alpha 2 v2 plus alpha k vk, and we get 0, maybe the word whenever is not necessary. If such a linear combination equaling 0 implies necessarily that all the alphas are 0. The only way to get 0 as a linear combination of these guys is when you just take 0 times each one of them. You can always do that, right? Okay? So this is precisely saying that there is no linear combination which is 0 where not all the alphas are 0. That's the complement to that definition. Clear? Okay. So let me give you one more example. So first of all, let's look back at the previous example we had. This was a linearly independent set, right? The only way to write alpha times this one plus beta times this one and get 0 is you have to take alpha 0 and beta 0. Do you see that? Okay, that's the only way to make a linear combinations of these two and get 0. Does everybody see that? Everybody? Okay. Whereas this was a dependent set of vectors because we saw that there is a linear combination which gets 0 where not all the coefficients are 0, namely this. Right? Look at this board, please. 2 times this one plus 3 times this one minus 1 times this one is 0. Do you agree? Okay. So here's another example. One more example. And with that, we're going to end today. And next time, we're going to write a theorem, which is going to kind of characterize all kinds of situations of linear dependence and linear independence. We're going to do that. And then we're going to do some examples of how we determine if a set is linearly independent or not. And guess what? To what is it going to be related? To systems of equations and to row reduction on matrices. Okay? But in a different way. Okay, we'll see that. So here's another example. Let's take a bunch of polynomials. So P1 of x is going to be 2x minus 1. P2 of x is going to be 2x squared minus 1. And P3 of x is going to be 3x squared minus x minus 1. So these are 3 polynomials in the set of polynomials of degree 2 or less over R. Okay? So we denoted it. So these 3 belong to R2 of x. Right? Polynomials of degree less than or equal to 2. Good? Okay. So I'm not going to show you how I get this, because this relates to what we're going to discuss next time, how we determine. But here's the fact. P1 equals 3P2 minus 2P3. Okay, let's do it precisely. P1 is 2x minus 1. This equals 3 times 2x squared minus 1 minus 2 times 3x squared minus x minus 1. You can verify this. So you have 6x squared minus 6x squared gone. Minus 3 plus 2 is this minus 1 here. And then plus 2x. Right? So do you agree to this? So P1 is a linear combination of P2 and P3. Right? Or you can move this to the other side and say 3. So another way of saying this is 3P2 minus 2P3 minus P1 equals 0. So here's a not all 0 coefficients linear combination of the 3 that gives 0, from which it follows that this set P1, P2, and P3 is not linearly independent, is linearly dependent. Good? Okay, so next time a theorem with some proofs and examples on how we determine, how we get to this, how we find the linear combination with non-zero coefficients that gives us the linear dependence, or how we decide that in fact they're independent. That's all next time.